Good morning. Today, our topic of discussion is nuclear models, especially liquid drop model. Why we are studying nuclear models? Let's move on to the first question. Why is the binding energy per nucleon almost constant? We had studied the binding energy curve, isn't it? Where we got the variation of binding energy per nucleon with mass number, and we had got a curve like this, where here this is an increasing curve and almost here the value is constant, so that all the nucleus will try to achieve this position, isn't it? From where did we got this curve? We don't know. So we are studying more about the nuclear structure so that we will get more information about binding energy per nucleon, and we will derive the formula and we will see how the graph is formed like this. Also, the second question is, why do certain nuclei emits alpha and beta particles? Because we know that the nucleus doesn't have alpha and beta particle inside it. Then how the nuclei is able to emit these particles? Now, the third question is, there are some nuclei which are more stable than other nuclei. Some nuclei means they are having the nucleons number 2, 8, 20, 28, 50 and 82. So the nucleus having either proton number or neutron number with these values, that is 2, 8, 20, 28, 50, 82, are more stable, and these numbers are known as magic numbers. So the nucleons with either proton number or neutron number belonging to these values will be more stable. Why? So the answer to these questions will be available after this class. Like any other quantum mechanical system, a nucleus also exists in its excited state. We know that an atom can go to an excited state. An electron can attain a higher state, isn't it? Similar to that, a nucleus also exists in excited state. And the most stable state will be obviously the ground state, and in which all the more of the nuclei will be generally found. So we can have the answers to these questions by studying different models. Different models like liquid drop model, shell model, collective model and optical model. Today we are going to deal with liquid drop model. So let's see how many nuclear models we have. So the nuclear models are classified into two. First one is independent particle model. By the name itself, the nucleons move independently in a common nuclear potential. Example for this is shell model. And the second type of nuclear model is strong interaction model, in which the nucleons are strongly interacted or strongly coupled together. And this strong interaction model include our today's topic, liquid drop model. And this liquid drop model is so successful in explaining the nuclear mass, nuclear fission, and also it will give you the answer to our first question, that how we got the binding energy curve as such. So it also derive the binding energy formula, that is binding energy per nucleon, and we can plot and we will be able to attain that graph. So in our module we are studying both the liquid drop model and shell model. And why we are studying models, nuclear models? Nuclear models will describe the structure of the nuclei and also their behavior. So moving on to our topic, liquid drop model or simply water drop model. This liquid drop model of the nucleus was first suggested by Bohr. He, along with Wheeler, explained the process of nuclear fission. So the theory is known as Bohr's and Wheeler's theory of nuclear fission. Let's move on to the basic assumptions of the liquid drop model. See, as the name indicates, liquid drop model or water drop model, the nuclei is considered as a liquid drop. So the first assumption is that the nuclei of all elements are considered to behave like a liquid drop of incompressible liquid of very high density. So they compared nucleus with that of a liquid drop. How? There are several similarities between a liquid drop and a nucleus. First point, see, we know that the small drops of liquid acquire spherical shape. In the case of liquid, there are two forces acting on it. In the case of a liquid drop, there are two forces acting on it. First one is the surface tension force, which is acting towards the center, which will try to give the liquid drop a spherical shape. So that is the first force, that is the surface tension force. Second force is the gravitational force, and you know that this gravitational force acting vertically downwards. What it will do? It will tend to flatten the liquid drop. So the two forces, surface tension forces acting towards the center, which will try to give it a spherical shape, and the second force is the gravitational force, which is acting vertically downwards, which will try to flatten the liquid drop. And ultimately it is the balance between these two forces that decides the shape of the liquid drop. So in the equilibrium state, the second point, in the equilibrium state, the nuclei of atoms remain spherically symmetrical under the action of the strong attractive nuclear forces, just like the liquid drop, which is spherical due to surface tension. So in the case of a liquid drop, we know that these surface tension forces and the gravitational forces balance each other so that the drop will acquire a spherical shape. Now what about a nucleus? Nucleus is also having two kinds of opposing forces within it. One is the strong attractive nuclear force, and second one is the repulsive electrostatic force between the protons. So two opposing forces are there inside the nucleus. Attractive nuclear force and repulsive electrostatic force between protons. So again, there will be a balance between these two opposing forces, and it decides the stability of the nucleus. Okay, so in the case of a liquid drop, two forces are surface tension forces and gravitational force. In the case of a nucleus, attractive nuclear forces and repulsive electrostatic force between the protons. So we can compare a nucleus with that of a liquid drop. Now the second point is that the density of the nucleus is independent of its size, just like the density of liquid, which is also independent of size. We know that the density of a liquid is constant, isn't it? Similarly, the density of a nucleus is also a constant and it is independent of size. So due to this similarity, we can compare nucleus with that of a liquid drop. Now we know that third point is that the molecules of a liquid are in continuous random motion. So that the molecules, these molecules when get heated will be evaporating. So on heating, the molecules which is under thermal motion will evaporate from the liquid. Similarly, the nucleons inside the nucleus are in a continuous motion, so that there is a spontaneous emission of alpha particles, which is similar to the evaporation of molecules from a liquid. So the third comparison is that the molecules in the liquid are in continuous motion, so that when temperature is increased, the molecules got escaped from the liquid in the form of evaporation. And in the case of nucleus, nucleons are in a constant motion and there is a spontaneous emission of alpha particles from the nucleus, similar to that of an evaporation in liquid. So because of these three similarities, we can compare a nucleus with that of a liquid drop. And we know that the binding energy per nucleon of a nucleus is constant, just like the latent heat of vaporization of a liquid, which is another similarity. The liquid is having a constant latent heat of vaporization, isn't it? Similarly, the nucleus is having a constant binding energy per nucleon. That's another similarity. So because of these similarities, we can compare a nucleus with that of a liquid drop. See, this is how liquid drop model has explained the process of nuclear fission. We know that nuclear fission is the process in which a heavy nucleus splits into two lighter nuclei. See, we consider nucleus as a sphere, isn't it? So sphere, this is the first stage of nucleus in which the nucleus is in spherical shape. Spherical shape means it is having least surface energy and greatest Coulomb energy. The Coulomb energy is more, so that the nucleons are tightly bound inside the nucleus due to this greatest Coulomb energy. So that the nucleus is attaining a spherical shape here. Now, what happens to this nucleus? The spherical nucleus has changed to this form. That means which looks like an oval shape, that is, which is more named as prolate spheroid. So in this case, the surface energy will be more and the Coulomb energy will be less. What happens when the Coulomb energy is less and the surface energy is more? See, the molecule is free to move. The molecules inside the liquid is free to move, isn't it? Similarly, the nucleus is attaining a oval shape here. Now, what happens? The Coulomb energy wins over surface energy. That means if the proton number is increased, what happens? There is an electrostatic repulsion between the protons inside the nucleus, which will tear the nucleus, or which will tend to cut the nucleus into two, so that the nucleus will have a dumbbell shape like this, which is known as scission. And at last, due to the higher Coulomb energy, this nucleus will split into two, so that two new nuclei is formed, and this process is known as nuclear fission. So all these states depends on the surface energy and the Coulomb energy nucleus has. So let's move on to our theoretical part. From here we are trying to calculate the binding energy per nucleon of a nucleus. For that, we are considering the different types of energies a nucleus can have. And we will derive a semi-empirical mass formula which help you to calculate the mass of a given nucleus. And this formula was derived by von Weizsäcker in 1935, and he used the assumption of the liquid drop model for a nucleus. So he first considered the volume energy. That means we are going to calculate the binding energy of the nucleus, and the binding energy of nucleus is due to volume energy, surface energy and Coulomb energy according to liquid drop model. So already we had discussed about the surface energy and Coulomb energy here. Now there is one more energy which is known as volume energy. So starting from this we are entering into the derivation part. So volume energy. We know that this liquid drop model in which a nucleus is considered to be a liquid drop, and this model comes under strong interaction model. Strong interaction model means the nucleons inside the nucleus are interacting with its neighbors. So as a first approximation, we can think of each nucleon in a nucleus as interacting solely with its nearest neighbors. So we can think of two nucleons. Nucleons means either proton or neutron which are inside the nucleus. So think of the energy that is associated with two nucleons. So think that we are having two protons. So there is an interaction. This is a strong interaction model, isn't it? So two protons is having an interaction between them, and that the energy related with these two protons is given as U, capital U. So the energy associated with each nucleon bond is given as U. So this is the energy between two nucleons. Now what will be the energy of each nucleon? So this U is shared between two nucleons, isn't it? So what will be the energy of each nucleon? It will be U by 2. So because each bond energy is shared by two nucleons, therefore each has a binding energy of half U or U by 2. Now think of a nucleon which is inside the nucleus. How many neighbors it will have? You can think of this picture. See, in a tightly packed assembly of identical spheres, these are protons and neutrons. Tightly packed protons and neutrons. So you can think of an interior sphere. This interior sphere is in contact with 12 other spheres. That means each nucleon is having an interaction with the 12 other nucleons. So that when an assembly of spheres of small size is packed together into a smallest volume, each interior sphere has 12 other spheres in contact with it. So we have the bond energy U, and each nucleon is having a bond energy U by 2, and this U by 2 is shared among 12 other neighbors, isn't it? So you have to calculate it as 12 into 1 by 2U, which is equal to 6U. That means each interior nucleon in a nucleus has a binding energy of 12 into half U, that is 6U. And in generally, a nucleus consists of mass number, that is the total number of nucleons inside the nucleus is A. So generally the total binding energy will be 6 into A into U. 6 AU. That is the volume energy given as EV, which is equal to A1 into A. So 6 into U is a constant. So it is given as A1. So A1 into A. And we know that this is the volume energy. The nucleons are inside a volume. So that is the energy due to the nucleons which is inside a particular volume. And we know that this nucleus is spherical. So that it contains a number of nucleons. So its volume include a number of nucleons. That means volume is, if capital R is the radius, what is the nuclear volume? It will be 4 by 3 pi r cube. So 4 by 3 pi r cube is proportional to A. So we got the first expression for the volume energy EV, which is equal to A1 into A. Now the volume, since this volume includes or encloses a number of nucleons, we can make this volume proportional to A, that is 4 by 3 pi r cube is proportional to A. Now the next is, we know that so the volume includes all the nucleons. Now some of the nucleons are there on the surface of every nucleus, isn't it? See, here this is the nucleon which is inside the nucleus, and so that it can interact with the 12 nearest neighbors. Now this is the nucleon which is on the surface of the nucleus, so that it can interact with less than 12 nucleons. So that the energy due to the surface nucleons is given as surface energy. So that the surface energy is proportional to the surface area the nucleus contains. So we can substitute surface energy as proportional to surface area. If capital R is the radius, what is the surface area? It is 4 pi r square. Now we know the equation for finding out the radius capital R. It is R0 a raised to 1 by 3. So substituting that, what you will get? 4 pi R0 a raised to 2 by 3. So 4 pi R0 is a constant. So we can write it as A2 into a raised to 2 by 3 with a negative sign. Why there is a negative sign? Because the surface energy will decrease the binding energy of the nucleus. So that a negative sign is shown. See, inside this nucleon is interacting with the 12 nearest neighbors. So they are interacting means they are tightly bounding the nucleons together, so that the nucleus is having high binding energy, so that the volume energy was positive. But the surface energy, due to the surface energy, what happens? The binding energy is getting decreasing, so that we are putting a negative sign. So the surface energy is equal to minus A2 a raised to 2 by 3. So surface energy is proportional to mass number raised to 2 by 3. And this surface energy is important for lighter nuclei, because lighter nuclei means the nuclear size will be small, isn't it? So most of the nucleons will be on the surface. So the surface energy is more important for lighter nuclei. Now the third energy is the Coulomb energy. From where this Coulomb energy will come? Due to the repulsive force between the electrostatic repulsive force between the protons which inside the nucleus. So the repulsion between each pair of protons in a nucleus also contribute towards decreasing its binding energy. See, binding energy means it will try to bind the nucleons together. But if the protons number is increasing in the nucleus, what will happen? The protons will repel each other, isn't it? That will decrease the binding energy of the nucleus. So here we are going to calculate the Coulomb energy due to the repulsive protons inside the nucleus. So we know that how to calculate the potential energy of the two protons which are separated by a distance r. So we are considering, first we are considering the potential energy of a pair of protons, and we will multiply it with the total pair of protons, so that we will get the total Coulomb energy. Okay, so the Coulomb energy is the work done to bring Z protons from infinity to the nucleus. So now think that we are having a pair of protons which are separated by a distance smaller. So what is the potential energy? Potential energy is the work done, and it is, we know we had studied the formula V as minus E square by 4 pi epsilon 0 R. So this is the potential energy of a pair of protons. Now think how many proton pairs will be there in a nucleus. If its proton number is given by Z, we know that the proton number is specified by Z, isn't it? Now how many pairs of protons will be there? We can calculate with this formula, that is Z into Z minus 1 by 2. So if Z is we know that Z is the number of protons, isn't it? So Z into Z minus 1 by 2 pair of protons will be there inside a nucleus. You can check it with by giving the values Z equal to 2, Z equal to 4, etc. So you will find, you can substitute and can find out how many pairs of protons will be there by substituting the value of Z. So V is the potential energy of a pair of protons, and the total number of pair of protons is Z into Z minus 1 by 2. So what will be the Coulomb energy? Total energy will be Z into Z minus 1 by 2 into V. So it is minus Z into Z minus 1 E square by 8 pi epsilon 0 into 1 by R. See, this 1 by R is given as an average here. See, we know that the nucleus is having a maximum radius capital R, isn't it? So we can replace a small r with a capital R also. So 1 by R is proportional to 1 by capital R itself, because the maximum nuclear radius is capital R. And we know that we know the relation that R is equal to R0 a raised to 1 by 3. So substituting the value of R here, we will get 1 by R0 a raised to 1 by 3. That means it is proportional to 1 by a raised to 1 by 3. So we got the Coulomb energy EC as minus A3 into Z minus 1 by a raised to 1 by 3, where A3 is the constant which we had substituted for this, that is 1 by 8 pi epsilon 0 E square. All the constants are given the name A3 with a negative sign, because we know that the Coulomb energy is negative, because the Coulomb energy will decrease the binding energy of the nucleus. So we have got the expression for volume energy, surface energy and Coulomb energy. Now we can total it, so that the total binding energy EB is equal to EV volume energy plus ES surface energy plus EC Coulomb energy. So A1A volume energy which is positive, surface energy A raised to 2 by 3 and Coulomb energy A raised to 1 by 3. So surface energy and Coulomb energy will decrease the binding energy as these terms are negative. Now this is the total binding energy, and we had plotted the graph in binding energy per nucleon. Per nucleon means EB must be divided with A, so that it will give you binding energy per nucleon. So EB by A, binding energy per nucleon. So divide this whole equation with A, so that you will get A1 minus A2 by A raised to 1 by 3 minus A3 into Z minus 1 by A raised to 4 by 3. So this is the binding energy per nucleon formula, and you can plot this values. See, we have got the binding energy curve like this, isn't it? So let's see. First we had calculated the volume energy, and volume energy, you know that the equation for volume energy is A1 into A. That means with respect to A, the graph will be a constant, isn't it? We are plotting A along x-axis, and this is binding energy per curve, and it is a constant. See, binding energy per nucleon is a constant given by A1. So the volume energy is a constant graph. Now, second one is surface energy. Surface energy, you know that this graph binding energy per nucleon is proportional to 1 by a raised to 1 by 3. So that the surface energy curve will be like this. And the third energy is Coulomb energy, in which the term is 1 by a raised to 4 by 3. Volume energy is proportional to a raised to 4 by 3. So, not volume energy, Coulomb energy. So, the Coulomb energy graph is like this. So, the individual graphs you can see this of the surface energy, Coulomb energy and volume energy. On totaling these graph, you will get a curve like this, which is known as total energy, binding energy per nucleon, plotting mass number along x-axis and binding energy per nucleon. See, this graph is similar to earlier graph, isn't it? So how we got this graph is explained with the help of the liquid drop model by deriving the semi-empirical mass formula. But this is not complete, because even though we had considered surface energy, volume energy and Coulomb energy, there is some corrections has to be made after this, and that corrections are done by including asymmetry energy and pairing energy. So the corrections to the formula has been done, and first we consider the asymmetry energy. We know that the nuclei having equal number of protons and equal number of neutrons are more stable, and therefore they possess maximum binding energy. So what happens when the neutron number is increased? When neutron number is increased, it will decrease the binding energy and it causes instability. And this is called asymmetry energy contribution to the binding energy. So the first correction to the formula is asymmetry energy, which arises due to the higher number of neutrons inside the nucleus. We know that neutrons and protons are like electrons. That means they are having spin half. We had already told in the first slide that nuclear energy states also exist. How we can plot the nuclear energy states? With the help of the proton number and neutron number. We already know, we had studied, we can plot the electrons energy levels. Similarly, we can plot the energy levels for both neutrons as well as protons, because neutrons and protons are fermions with spin half, and they will obey the Pauli's exclusion principle. So moving on to our asymmetry energy. Asymmetry energy comes when there is more neutrons are there in a nucleus. So these are the energy levels plotted here of that of a proton and neutron. See, let's study this picture. Here you can see that these are the neutrons and these are the protons. And here neutrons are of 12 number and protons are of 18 number. So if proton number is equal to neutron number, we know that this nucleus is stable. That is, if n is equal to z is equal to 8, the nucleus is already stable. But here n is equal to 12, the number of neutrons is equal to 12 and number of protons z is equal to 8. And it is arranged in a sequence that each energy levels consist of 2 protons and 2 neutrons of opposite spin. See here, spin up, spin down, spin up, spin down. Similarly, each energy level consists of 2 neutrons and 2 protons of opposite spin. And each energy is, see, along y-axis energy is plotted, and each energy level is having energy epsilon. That means the energy difference is epsilon. So n is equal to 12 and z is equal to 8. So this is the case where neutron number is greater than the proton number. So n equal to 12 and z is equal to 8 means n minus z is equal to 4. And these 4 neutrons has occupied a higher energy state. See, from here to here the neutrons had more occupied. So this energy state is epsilon, and the next energy state is epsilon. So they had occupied a higher energy state of 2 epsilon. Isn't it? Now we know that n minus z is equal to 4. So generally you can write the 2 epsilon, that is the neutrons had occupied a higher energy state of 2 epsilon. So write 2 epsilon as 4 into epsilon by 2. Now 4 can be written as half into n minus z. That means half into n minus z, that is 4 neutrons would have to replace proton. I repeat, when the neutrons, we are going to calculate the energy difference, delta E. How we can calculate the energy difference? We can calculate the number of neutrons, and what is the energy increase per neutron, we can calculate and we can multiply, so that we will get the energy difference delta E. So delta E is obtained as number of new neutrons into energy increase per neutron. Now, what is the number of new neutrons? Number of new neutrons is given as n minus z by 2. Now, what is the energy increase per new neutron? We know that the energy increase is epsilon and epsilon, that is 2 epsilon, which is written as 4 into epsilon by 2. Now how we can write 4? 4 as half into n minus z. So half into n minus z into epsilon by 2. So it is multiplied with, so epsilon by 8 into n minus z whole square. Now what is n? N is the number of neutrons. How we will get it? From subtracting z from a, isn't it? Because n is equal to a minus z. So n is substituting n is equal to a minus z here. N minus z whole square will be a minus 2z whole square. So we got a delta E as epsilon by 2 into a minus 2z the whole square. So we had given the constant as A4 minus A4, so that minus A4 into a minus 2z the whole square divided by a. So that is the asymmetry energy due to the difference in number between n and z. See, from where this A came, the greater the number of nucleon in a nucleus, the smaller is the energy level spacing. And this energy is proportional to, so that we can write is epsilon is proportional to 1 by A. So that 1 by A also came here in the formula. See, when the number of nucleons increases, the nucleons will attain higher energy, isn't it? And higher energy is, so that it is proportional to 1 by A. So minus A4, a minus 2z whole square divided by A. So that is the asymmetry energy, and this asymmetry energy will decrease the binding energy of the nucleons, so that it is given a negative sign. Now the last correction to the formula is pairing term. And this correction term arises from the tendency of proton pairs and neutron pairs to occur. So the proton pairs and neutron, we can analyze the proton pair and neutron pair so that we can form the pairing energy. We know that even nuclei are more stable and are having more binding energy, so that the pairing energy is positive because they are more stable, isn't it? So they are more stable, so that pairing energy is positive for even nuclei. See, some figures are given. You can check for the proton number. See, here boron 5, 10 is given. So the proton number is 5 and neutron number is also 10 minus 5, 5. So 5 and 5 means they are equal. But the example is odd. And here you can compare the other, you can check for the other values also. So pairing energy is the energy which arises due to the proton and neutron pairs. If the proton number and neutron number are even, the pairing energy is positive. And the pairing energy is 0 for odd even and even odd nuclei. And the pairing energy is negative for odd nuclei. So taking these three values, see, positive, if even proton and neutron numbers are even, the pairing term is positive. If a proton and neutron number are odd, it is negative. And if it is even or odd even, the pairing term is taken as a 0. So depending upon the number of protons and number of neutrons and checking whether it is even or odd, we can form the pairing term. See, so the pairing term is given by the relation EP is equal to plus value is there, minus value is there, and 0 value is there. So plus or minus, comma 0. We don't have the derivation for this pairing term, so that you can study the formula by itself, that is A5, the constant term, divided by A raised to 3 by 4. You have to know that this pairing term is proportional to mass number as A raised to 3 by 4, inversely proportional to A raised to 3 by 4. Thus, we can add this corrected formula to the binding energy formula and forms the semi-empirical mass formula, SEMF. So that is binding energy. So we are writing the binding energy, not binding energy per nucleon. So this is binding energy. A1A minus A2A raised to 2 by 3 minus A3 is Z into Z minus 1 by A raised to 1 by 3 minus A4 A minus 2Z whole square by A plus or minus 0 A5 by A raised to 3 by 4. See, you are given the values of the constants A1, A2, A3, A4 and A5 values are given, the constant values, and the first term belongs to the volume energy, second is surface energy, third is Coulomb energy, fourth one is asymmetry energy, and the fifth one pairing energy. So these forms the semi-empirical mass formula with all the constant values. So with this theory, now you can do a problem that the atomic mass of a zinc isotope Zn3064 is 63.929 AMU. So you know the value of capital A from here. Capital A is 64. See, the A value is known. Now you can calculate its binding energy using semi-empirical mass formula and compare the results with the direct formula. See, the semi-empirical mass formula is given. You have to substitute only A here. All the values are given. Z, you can calculate the number of protons from here. The number of proton is 30. Capital A is 64. You can substitute all these values and substitute the constant values A1, A2, A3, A4 and A5, and you can find out the binding energy using the semi-empirical mass formula. Now you can compare that result with the direct formula. What is the direct formula? You have given the atomic mass, isn't it? You can calculate the mass defect delta M and multiplied with the C square, you will get the binding energy. So in that way also you can calculate the binding energy and can compare the results. Okay, do it by yourself. So this is the next problem where the isobars are nucleides having same mass number A. Now you can derive a formula for the atomic number of the most stable isobar for a given A and use it to find the most stable isobar of A is equal to 25. See, we are given, we have to derive a formula for the atomic number of the most stable isobar. See, to find the value of Z for which the binding energy is maximum. Binding energy is maximum means that taking the derivative will be 0, isn't it? With respect to Z. So, you can take the derivative of that binding energy and can equate it to 0 and can find out the value formula for Z. So, that is the first part. And now you can substitute A is equal to 25 here and can substitute the whole values and can find out the value of Z, and that Z is 12, that is magnesium with a Z12 and mass number 25. So two parties there. First to find out the equation for Z. Now you can substitute A as 25 here and we will get the value of Z as 12. Now moving on to the advantages, disadvantages of the liquid drop model. Advantages are it explains the binding energy. Now we have know that with the help of liquid drop model we had derived the binding energy formula, isn't it? So we can calculate the binding energy of all the nuclei using this liquid drop model. Second one, we had explained the nuclear fission with the help of Bohr's and Wheeler's theory, isn't it? So the liquid drop model is successful in explaining the nuclear fission and nuclear fusion process. And also we had a initial question that how the alpha particles got emitted from the nucleus, isn't it? So the liquid drop model also explains the energies of radioactive decays also. Now we had already studied that fission is explained with the help of a liquid drop model. So also nuclear fusion is also explained with the help of this water drop model. Now, main drawbacks of the liquid drop model is that liquid drop model is not able to explain the magic numbers. I had already told that 2, 8, 20, 28, some numbers, isn't it, that are magic numbers. That means the nuclei that contain that number of protons or neutrons are more stable. So the liquid drop model was not able to explain the magic numbers with its theory. Also, it is not able to explain the excited states of the nucleus, and also it's not able to calculate the nuclear spin. We had just told that the nucleons are like electrons, that is having spin half, and they are fermions. But using liquid drop model, we are not able to calculate the nuclear spin. So these are the drawbacks of the liquid drop model. So even though the session was lengthy, I think the session is clear to you. Thank you.